Hello and welcome to today's video. In today's video, we'll be talking all things scientific notation, including how to convert into scientific notation, Sig Figs with scientific notation, what is scientific notation. There will be lots of examples and a self-quiz at the end. So what is scientific notation? Scientific notation is a way of rewriting a number in a shorter and more convenient form. So here on the left, you can see numbers in the standard form. They're what you're probably used to seeing numbers written out like. And if you go over to the right, these are examples of the same numbers in scientific notation. So you can see it's a lot more abbreviated and more convenient, which is why you would use scientific notation. You use it to make it easier on you because it makes really small numbers and really big numbers a lot more manageable. Look at how many zeros are on that. That's a lot to type out and to write out in math problems. Also, it allows for less room for errors. Let's take those two numbers in the first bullet point, for example. Let's say you're writing these numbers out in a math problem. How likely could you be to add an extra zero in there or maybe delete a zero when you're writing or typing it out in your calculator? Scientific notation helps eliminate a lot of errors. It also allows for fast comparison of numbers by looking at the exponential power. Let's say you are given two numbers, 10 to the 8th and 10 to the 7th. Here, you can immediately tell that 10 to the 8th is bigger because the exponent is bigger. However, if you were given the same numbers written out, 1, 2, 3, 4, 5, 6, 7, 8 versus 1, 2, 3, 4, 5, 6, 7, it would be a lot more difficult to see quickly which one is bigger without counting all the zeros. So let's see for yourself. What's easier, writing or inputting 3.78 times 10 to the negative 6 in your calculator or 0.0000378? I think the answer is clear. Now let's talk about scientific notation rules and actually how to convert and the rules behind it. So in scientific notation, this is going to be the basic form for all of scientific notation. So there's going to be a coefficient times a base and then an exponent. So let's go through these rules one by one. So the first rule with the coefficient must have exactly one non-zero digit to the left of the decimal point if there's a decimal present. Now let's look at this box right here of examples, and I'll break down that first rule so you can see the example. So in all of these, you'll see that there is one number to the left of the decimal point. So I'll just put a little highlight the decimal, and you'll see that there's only one number to the left, and then the remainder of the numbers follow after the decimal point. And then in this last example right here, there's only one number and there's no decimal point. So that just shows you this little if a decimal is present. If there's no other numbers, then it would just be one number. But if there's multiple numbers, there will always be one in front of the decimal and then the rest will follow. The coefficient always also will include all significant figures of the number. So here you can see that all of the significant figures in the number are in this purple coefficient. And right now is actually a really good time to pause the video and go check out one of my previous significant figures videos if you need a refresher or aren't sure what Sig Figs are. It's really important for scientific notation to have a good grasp on that. So you'll see in this first example that this number has 2 Sig Figs. And then the next example has 3 Sig Figs, and the last example has 1 Sig Fig. And then you'll notice that the same amount is in the scientific notation version in the coefficient. So here there's 2 Sig Figs still. In the next example, there's 3 Sig Figs still. And then in the last example, there's 1 Sig Fig. So in scientific notation, the before and after, it should have the same amount of Sig Figs. It needs to in order to be accurate. Okay, then the next rule is about the base. And the base is always going to be 10, which makes it pretty easy. So this red thing right here, the number will always be 10. So you can see 10, 10, 10. And that's just the rule. That's always how it's going to be. And then the last rule is about the exponent. So the exponent can be any non-zero integer, positive or negative. So it doesn't matter. And here in the examples, you can see we have a 4, a -3, and a -5. Basically, it has to be a whole number, so it can't be a fraction, and it can't be 0, because that would just make that 1, so it wouldn't be scientific notation. But it could be a positive 2005 or a negative 100. It doesn't matter, positive or negative, as long as it is a non-zero integer. Okay, so now let's put this into practice and actually convert in and out of scientific notation. So I think it's easiest to start with something that's in scientific notation and convert back into standard form for you to see how we get the essence of it, and then we'll do examples from standard form into scientific notation. But this, I think, will really help us all get on the same wavelength and understand more of the process behind it. So these numbers are both written out in scientific notation, and you'll see the only difference is a positive 7 in the exponent versus negative. But let's do this example first on the left. So if we take 9.48 and multiply by times 10 to the 7th, that's saying it's 9.48 times 1, 2, 3, 4, 5, 6, 7. Okay, so that is literally what scientific notation is saying if you expand it out. But a little hack, if you do that in your calculator, or you could add zeros, but something that we're going to do here is 9.48. We are going to move this decimal place over 7 spots because it's telling us to move to the right 7 spaces because it's a positive 7. So what we're going to do is we're going to go 1, 2, 3, 4, 5, 6, 7, and add zeros in. And that is our final answer once we move this decimal place over there. So it would be without this decimal place then. And this would be the final answer in standard form, which is what you see there. So this is the standard form of this number, and this is scientific notation. And that just breaks down how we transition from those and kind of like breaks it down easier to see in the math behind it and not just a theory. Okay, now let's do the next example. So again, we're going to put a 9.48 and we are going to move it to the left 7 spaces. And we're going to the left because it's a negative exponent, so the number is becoming smaller. And when I say move it, I mean the decimal place. So here, we are going to move this decimal place over 1, 2, 3, 4, 5, 6, 7. And then we'll plop that decimal point right there, and we'll add the zeros in. And because you're moving it, let's delete that. And that is the answer. So again, we went from scientific notation to the standard form because I think that's easier to show you. And now let's do some examples from the standard form going into scientific notation. Okay, so like we said in the scientific notation rules, all the numbers are going to start with one number to the left of the decimal point. So I'm just going to set that right there so that we can kind of think about this. So in this number, we are going to set the decimal point right there, and we're going to again move the decimal until we hit where the actual decimal actually is in the value. So if we move this, it would be 1, 2. So if we take 4.218 times 10 squared, that's how you would transition. This would be the scientific notation of the standard value. So that's the scientific notation value of 421.8. Now let's do the next example. So now we have 0.0004218. So again, we're going to put a decimal to the, there's only going to be one number in front of that decimal point, and we're just going to move this decimal point over until we hit the actual value of the decimal. And in that case, there was 4 spots. So we're going to do 4.218 times 10 to the negative 4 because we're moving to the left 4 spots to get the value of where we put the decimal versus the actual decimal. And again, it's written out like this because in scientific notation, there's only one number in front of the decimal point and all of the rest follow. And you can see that's the answer. Okay, this is a really good example showing the significance of Sig Figs. And again, if you haven't seen my Sig Fig video right now, you should pause the video and go check that out. Otherwise, this won't make much sense. So both of these values are valued at 23,000. The only difference is the number on the left has a 0.0 and the number on the right does not have that. But both of their values are the same. They're both 23,000. The only difference is the amount of Sig Figs that the numbers have. So the number on the right has on the left, 1, 2, 3, 4, 5, 6. 6 Sig Figs. And the number on the right has 1, 2. 2 Sig Figs. So because of the scientific notation rules, we know that the coefficients for the two numbers will be different because they differ in the amount of Sig Figs they have. So let's check this out. So again, we're going to put a decimal where we know it needs to be because there's only one number in front of the decimal point in scientific notation. And let's just move this over until we hit this decimal point. So we move it over 1, 2, 3, 4. So this number, we know it will be times 10 to the fourth because we just had to move the decimal point over there. But the coefficient, we can't forget about all of these numbers since they're all significant. So this coefficient has to be 2.30000 times 10 to the fourth. That is the scientific notation of this number, and that is because of the amount of Sig Figs that they have. So here, if you look at the amount of Sig Figs in this, you will also see that it's 6 significant figures, which is super important. Okay, let's do the next example. So if you put our little decimal point there, our placeholder, and you're gonna move the decimal over to where the decimal point would be. Here you don't visually see one, but you know there would be one there because this is a full number and the decimal point would go there. So if we move that over 1, 2, 3, 4, you know that you would hit the same times 10 to the fourth. But what about the coefficient? So in this one, because there's only two significant figures, it is only 2.3 times 10 to the fourth. And again, you'll see this has 2 Sig Figs. One other thing I want to point out is that all of these numbers are the same number. They're the same value. So this number right here is the standard form, how you're used to seeing it. These two numbers are scientific notation. This one is in the raised form, and this one just has a little caret saying to the 5th exponent. So sometimes in calculators or other things, you'll see it written out like this, but it's the exact same as this. And then these E's basically are just condensed versions of that whole thing. So the E's are saying times 10 to the power. So you don't, with E's, you don't need to say like E to the 5th. That's a whole different thing because it's accounting for that exponent. They mean exponential. So those are all the same number. I just wanted to point that out because when I went to college, some of my professors used these and I had never seen it before and it confused me. Okay, now here is self-quiz time. So some instructions you could see for an example like this would be convert the following numbers given in standard form into scientific notation. So you can pause the video here and then unpause when you're ready for me to unveil the answers. Okay, and here are the answers to the self-quiz. If you have any questions, please comment them below. If you're confused about anything, as always, please check out my previous videos if you need help on anything else and comment below what you'd like to see next. Thank you.